When everything seems quiet, do you know about a spaceship that took off before you even took your first breath, still drifting in the darkness? It carries the story of how far humanity has come and how vast the journey ahead still is. It is hurtling through the darkness now, about 25 billion miles from Earth, farther than any object humanity has ever built. Yet this is an astonishing fact. Even at that incredible distance, this probe would still need 73000 years to reach the nearest star outside of our Sunday. We are about to cross the boundaries of the familiar, to imagine ships propelled by nuclear fire, to encounter civilizations capable of harnessing the energy of entire stars. What follows has the power to fundamentally change how you view our place in the universe. Take a deep breath. This is where we begin. Imagine standing on the shoreline of an ocean that stretches endlessly in every direction, far beyond any horizon you can conceive. Many believe our solar system ends at Pluto, but that comforting idea is simply wrong. Far beyond that distant world of ice lies a region known as the heliopause, the place where the influence of our sun finally fades away. This unseen boundary sits roughly 11 billion miles from Earth, so distant that sunlight requires 16 hours just to arrive there. If you attempted the journey by car driving at highway speed, without ever stopping, it would take around 12 million years. Think of the solar system as an enormous bubble drifting through space, blown outward by the sun itself, through something we call the solar wind. This wind is a torrent of charged particles streaming outward at more than 1 million miles per hour. For billions of miles, it presses against the surrounding emptiness, forming a vast protective cocoon around everything we know. But even the sun's power has its limits. At the heliopause, this bubble collides with the harsh winds of interstellar space, where particles born around distant stars slam into our neighborhood like waves crashing against a seawall. Here, temperatures plunge toward absolute zero. The very nature of matter shifts. You have stepped beyond the influence of the only star our species has ever known. In 2012, Voyager 1 crossed this frontier, becoming the first human-made object to enter genuine interstellar space. Its radio messages now require more than 21 hours to reach Earth, longer than a full day. What it sends back are faint murmurs from a realm so alien that scientists are still struggling to interpret their meaning. And yet consider this. This boundary, which took 35 years for our fastest spacecraft to reach, represents less than 1/1,000,000 of the distance to the nearest neighbouring star. It is like taking a single step on a journey that would circle Earth 2.5 million times. That is how little of the road we have truly covered. The heliopause is not merely an edge, it is a warning. Beyond it, the rules we rely on no longer apply. The gentle warmth of our sun becomes irrelevant. The magnetic shields that protect us from lethal radiation disappear. Even time itself begins to feel different when travelling between stars at unimaginable speeds. Standing on this cosmic shoreline, it becomes clear that leaving the solar system is not just a question of faster rockets or clever engineering. It demands a transformation of who we are, a species capable of enduring the immense frozen darkness between worlds. And remarkably, our first emissaries into this strange domain are already returning the knowledge we will need. Now we follow humanity's boldest messengers into the unknown. Two golden records drift silently through the void, carrying the sounds of Earth towards civilizations we may never encounter. Launched in 1977, Voyager 1 and Voyager 2 were originally designed to study Jupiter and Saturn and then quietly fade into the depths of space. Instead, they became our first interstellar ambassadors, racing toward distant suns with messages from a small blue planet they will never see again. Each carries a golden record filled with the songs of whales, the cries of infants, and music from across the world, a message cast into the cosmic ocean. Voyager 1 moves at 38,000 miles per hour, faster than any spacecraft ever built. At that speed, a flight from New York to Los Angeles would take just 4 minutes. And yet, after 46 years of relentless motion, it has scarcely begun its voyage to the stars. It will not pass anywhere near another star for 40000 years. These probes are like the ships of medieval explorers sailing toward unknown lands. Their crews understood they might never return, yet they carried with them the hopes of everyone they left behind. The computers aboard Voyager possess less processing power than a modern phone. Still, they operate in conditions that would destroy any machine on Earth within seconds. The cold of interstellar space does more than freeze. It alters matter at the atomic level. Metal grows as fragile as glass. Electronics that function flawlessly for decades begin to fail in ways no engineer could foresee. Slowly the probes are dying. Their nuclear power sources weaken year by year. But even in their final years, these fading messengers have transformed our understanding of what lies beyond. They have revealed magnetic fields twisted into astonishing shapes by stellar winds. They have measured cosmic rays born from galaxy-shattering explosions that occurred long before Earth itself came into being. Most astonishing of all, we have learned that the space between the stars is not a true void. It is permeated by an exceedingly thin mist of hydrogen atoms, along with enigmatic particles left behind from the earliest moments of the universe itself. With each passing day, the radio whispers from Voyager fade a little more. By 2025, those signals will cease altogether, their nuclear power sources finally spent. The probes will drift on as silent apparitions, vessels without voices gliding through a sea of stars, bearing their golden records toward destinations we can scarcely imagine. Researchers suggest that in roughly 300 million years, long after humanity has either transformed into something utterly unfamiliar or disappeared entirely, one of those records could be discovered by an alien intelligence. They might listen to our music, our voices, our laughter. They would learn that once on a small blue world there existed a species, bold, perhaps reckless enough to cast messages into the vast cosmic ocean. Yet Voyager revealed something even more profound than what lies beyond our world. It proved that we are capable of building machines resilient enough to endure the journey between stars. The true question is not whether other solar systems can be reached. It is whether we ourselves can endure long enough to make that voyage. And that leads us to the most unsettling realization of all. Between us and the nearest star stretches a darkness so absolute it makes the deepest trench in Earth's oceans seem bright by comparison. Space is not merely empty, it is ferociously, violently empty in ways that strain the limits of human intuition. Shrink our solar system until Earth is no larger than a marble and the closest star would be about 1400 meters away. It would be like placing a marble in New York and expecting to strike another marble in Denver with a flawless throw. But the emptiness is not just about distance. Even in the finest vacuum chambers on Earth, engineers can remove nearly all the air, yet still leave around 10 million particles. In interstellar space, there is less than a single atom spread through a volume smaller than a grain of sand. Picture it this way. Imagine attempting to swim across an ocean so insubstantial you cannot feel the water at all. So cold it would freeze your blood within seconds, and so saturated with invisible radiation that it would unravel your DNA from the inside. That is the reality spacecraft encounter in the gulf between stars. This emptiness itself bends the rules of physics. With no air to carry vibrations, the universe becomes eternally silent. With virtually no matter to transfer heat, temperatures linger just above absolute zero, minus 450 degrees Fahrenheit. In such conditions, even helium solidifies. Metals fracture like glass. Electronics fail in ways scientists are still struggling to fully explain. The radiation environment makes Chernobyl seem almost benign. Cosmic rays forged by exploding stars and voracious black holes crash into anything in their path at nearly the speed of light. A single cosmic ray can carry more energy than a baseball thrown at 60 miles per hour, compressed into a region smaller than an atom. These unseen projectiles would tear apart human DNA, leading to cancer, neurological damage, and death within months. Worse still, the magnetic shield that protects life on Earth vanishes entirely in interstellar space. Stellar winds from distant suns generate electromagnetic tempests capable of destroying any electronics we might send. It would be like trying to use a mobile phone in a lightning storm that rages for centuries without pause. Perhaps most disturbing of all is that this emptiness is not uniform. The space between stars contains vast clouds of hydrogen gas, grains of cosmic dust, and elusive dark matter that we can detect but do not yet comprehend. These regions can extend for hundreds of light years, forming invisible barriers that could cripple or annihilate anything passing through them at tremendous speed. Traveling through interstellar space at velocities required to reach another star would resemble driving through a sandstorm at 200 million miles per hour. Each fleck of dust becomes a missile. Every gas cloud turns into a wall of devastation. And yet within this hostile void we have identified something that reshapes our vision of space travel entirely. Our next target makes this emptiness seem almost crowded. 4.25 light years away shines a star so faint it demands a telescope just to be seen, and yet it may hold the secret to humanity's future. Proxima Centauri, our nearest stellar neighbour, is a red dwarf, scarcely 1/8 the size of our Sun. If the Sun is a blazing bonfire, Proxima is a fragile candle trembling in the cosmic breeze. This diminutive star emits so little light that its potentially life-supporting planet receives only 1% of the energy Earth enjoys. But here is the detail that sends a shiver down the spine. That world, Proxima b, orbits within the Goldilocks zone where liquid water could exist. It lies just 4.25 light years away, almost next door by cosmic standards. At the speed of our fastest spacecraft, reaching it would require around 73000 years. For an immortal civilization, that would feel like a brief excursion. Think of Proxima Centauri as a lighthouse on a faraway shore. Its beacon is visible. Its position is known. Yet the ocean between us and that refuge is churned by storms, powerful enough to destroy any vessel we can currently imagine building. The star itself has a mass of only 12% of our Sun, and yet it erupts with stellar flares so violent they make the harshest space weather near Earth seem almost calm. In just a few minutes, these outbursts unleash more energy than our entire civilization has generated across all of recorded history. Those flares rain down on Proxima b with levels of radiation powerful enough to sterilize its surface completely and tear away any atmosphere it might once have held. If life exists on that world, it would have to retreat far beneath the ground or evolve forms of protection so effective they would render our most advanced technology little more than paper armor. Red dwarf stars like Proxima are astonishingly long-lived. They shine for trillions of years, hundreds of times longer than the future remaining to our own Sun. When our solar system fades away in 5 billion years, Proxima Centauri will still be glowing, even as the universe itself drifts toward cold darkness. It is in that sense the ultimate destination for any species determined to survive beyond the death of stars. But reaching it represents the greatest challenge humanity has ever confronted. Even travelling at 10% of the speed of light, far faster than anything we have ever built, the journey would still take 43 years. A full human lifetime spent crossing the vast emptiness between stars. Children born aboard such a ship would grow old and die without ever setting eyes on their destination. The energy needed to reach those speeds stretches the limits of imagination. You would have to convert matter directly into energy, just as Einstein described in his famous equation. The fuel alone would outweigh entire mountain ranges. And even if the energy problem was solved, decades of exposure to cosmic radiation during the voyage would be fatal to any human crew. And yet astronomers have already identified dozens of potentially habitable planets orbiting red dwarf stars within 50 light years of Earth. These ancient suns offer something our own star cannot: time. Billions of years for life to adapt, to explore, and to spread across the galaxy before the last stars finally burn out. Proxima Centauri is not merely our closest stellar neighbour, it is, in a very real sense, our cosmic life insurance policy. But reaching it would require us to confront the most fundamental speed limit in the universe. And this is where Einstein's insights overturn our intuitions completely. Nothing that has mass can ever reach the speed of light. And that single fact may condemn humanity to remain forever on one world. Einstein revealed that as an object approaches light speed, something extraordinary and deeply counterintuitive occurs. Its mass increases without bound, tending toward infinity. To accelerate even a single atom to the speed of light would require all the energy that exists in the universe. It is not merely impractical. It is mathematically forbidden, woven into the fabric of reality itself, a cosmic speed limit enforced by the laws of physics. Light travels at 671 million miles per hour. At that speed, you could circle Earth 7.5 times in 1 second. You could reach the moon in 1 1/3 seconds. You could cross the entire solar system in just 11 hours. And yet, even moving this fast, the journey to Proxima Centauri would still take 4.25 years. Think of the speed of light as the ultimate highway speed limit. Except here, the penalty for breaking it is not a fine. It is the collapse of physics as we understand it. As a spacecraft approaches light speed, time itself begins to slow relative to the rest of the universe. At 99% of the speed of light, 1 year aboard the ship corresponds to 7 years passing on Earth. This strange consequence is known as time dilation. A crew travelling to Proxima Centauri at nearly light speed might experience only a few months of flight time, while decades pass for everyone they left behind. If they could return, they would find their friends and families gone and their civilization transformed beyond recognition. They would become time travellers, stranded in a future they never chose. Yet even this scenario remains beyond our reach. The energy demands alone make it impossible with present technology. To accelerate a spacecraft with the mass of the space shuttle to just 10% of the speed of light would require the total energy output of the United States for more than 100 years. Reaching 90% of light speed would demand more energy than our sun produces in a century. And even if the energy problem was solved, the physics of high-speed travel becomes brutally hostile. At near light speeds, tiny grains of interstellar dust strike with the destructive force of nuclear weapons. The sparse gas between stars turns into a relentless storm of radiation that would vaporize any known material. The universe itself resists such journeys, and yet within Einstein's equations lies something truly remarkable. Although nothing can move faster than light through space, space itself can expand faster than light. The universe has been doing exactly that since the Big Bang. During the era of cosmic inflation, regions of space were carried apart faster than light could ever travel between them. There is a subtle gap in Einstein's equations that opens a doorway to something that feels like pure science fiction. We may not need to outrun light itself if we can persuade space to do the moving for us. Rather than forcing our way past the ultimate cosmic speed limit, we could allow the fabric of space and time to carry us along. Yet to exploit such a possibility would demand technology so advanced that to our eyes today, it would look indistinguishable from magic. Our earliest attempt to sidestep Einstein relied on the most ferocious force known in nature. Picture yourself balancing on a surfboard, riding a wave made not of water but of nuclear fire. Each detonation powerful enough to erase a city from the map. In the 1950s, Project Orion proposed what remains one of the boldest spacecraft concepts ever imagined, a vessel driven forward by the repeated detonation of atomic bombs behind an enormous steel plate. Every few seconds, another nuclear device would explode, hurling the ship onward with forces that would reduce ordinary materials to dust. Remarkably, the physics holds together. Nuclear explosions unleash more energy per pound than any reaction we know. One atomic bomb contains enough energy to supply New York City for 2 weeks. Link thousands of these blasts together, and you could drive a colossal spacecraft to 5% of light speed, fast enough to reach Proxima Centauri in less than 100 years. It is rather like the ultimate motorcycle, except instead of burning fuel, you are setting off hydrogen bombs every 3 seconds and surfing the resulting shockwave. Such a craft would require shock absorbers, as large as buildings, and a pusher plate fashioned from materials capable of surviving repeated nuclear impacts. Engineers showed that a ship weighing thousands of tons could still reach velocities that chemical rockets could never approach. The original Orion plans placed the crew inside a compartment wrapped in layers of lead shielding. Astronauts would endure brief episodes of crushing acceleration, followed by weightlessness as the ship drifted between detonations. It would be like sitting inside a colossal hammer, struck again and again by the hand of an angry god. But the radiation would be deadly. Each nuclear pulse would bathe the spacecraft in gamma rays, neutrons, and radioactive debris. Even with substantial shielding, the crew would absorb radiation doses that lead to cancer, infertility, and death. The vessel itself would become so contaminated that approaching it without protection would be fatal. Modern concepts of pulse propulsion replace fission with fusion, producing far cleaner explosions and far less radioactive waste. Fusion devices bind hydrogen atoms together, releasing energy directly from Einstein's famous equation, while leaving behind mostly harmless helium. These thermonuclear pulses could drive spacecraft to 10% of light speed, while keeping radiation exposure within survivable limits. Even so, the engineering challenges are immense. The pusher plate would have to endure temperatures of millions of degrees and pressures exceeding those at the center of Earth. The shock absorbers would flex and recoil like springs on a cosmic scale, each one taller than a skyscraper. Simply storing the fuel would require a magazine capable of safely housing thousands of nuclear devices. And yet computer models suggest that nuclear pulse propulsion is feasible with technology we already understand. This idea does not depend on exotic physics or hypothetical particles. It demands only engineering solutions to problems we know how to define. With sufficient commitment, an Orion-style spacecraft could be built within 50 years. The true barrier is not scientific. It is political. Constructing a vehicle powered by nuclear weapons would require global cooperation on a scale humanity has never achieved. Such a ship would be in effect a mobile nuclear arsenal powerful enough to devastate entire worlds. But if we are genuinely determined to reach the stars, we may have to grasp the tiger by the tail. Next, we turn to a gentler method, one that draws directly on the energy of the cosmos itself. Through the emptiness of space flows an unseen river of pure energy, and only now are we learning how to navigate it. Light carries momentum. Every photon striking a surface delivers a minute push, like countless grains of cosmic rain tapping on glass. The effect is extraordinarily weak. The pressure of sunlight at Earth amounts to the weight of a paperclip spread over an area the size of a football field. Yet in the frictionless vacuum of space, even such a delicate force can over time accelerate a spacecraft to astonishing speeds. Solar sails operate like sailing boats turned inside out. Instead of wind driving a hull through water, starlight pushes a sail through space. The sail must be impossibly thin, thinner than a soap bubble, lighter than the wings of a butterfly, yet robust enough to survive the voyage between worlds. Imagine wrapping a spacecraft in aluminium foil, so fragile it could tear at the touch of your breath. Japan's Icaros mission demonstrated that this is more than theory. Launched in 2010, the experimental probe deployed a sail the size of a basketball court and successfully maneuvered through space using nothing but the gentle pressure of light itself. The sail measured just 7/12,000ths of an inch in thickness, so impossibly fine that stacking 14,000 sheets together would only match the width of a single human hair. Yet this is where solar sails truly begin to astonish. They do not consume fuel. Chemical rockets exhaust their propellant within minutes and then simply drift. Nuclear rockets demand vast quantities of radioactive material to function. A solar sail, by contrast, keeps accelerating for as long as starlight falls upon it, steadily gaining speed over months and years, eventually surpassing anything any rocket has ever achieved. The Breakthrough Starshot project aims to exploit this idea to reach Proxima Centauri in just 20 years. Rather than relying solely on sunlight, the plan is to propel minuscule spacecraft using the most powerful lasers ever built. A ground-based laser array producing 100 billion watts would concentrate its beam onto sails no larger than postage stamps, driving them to 20% of light speed in only 2 minutes. These star chips would weigh less than a paperclip, yet they would carry cameras, computers, and communication systems. Hurtling through interstellar space at 134 million miles per hour, they could image the planets orbiting Proxima Centauri and transmit those pictures back to Earth. A voyage that would take Voyager 73,000 years could instead be finished in just 20. But expanding solar sails to transport human crews introduces challenges that stretch engineering to its limits. A sail capable of carrying people would need to span hundreds of miles larger than most nations on Earth. Holding such a delicate structure together while accelerating at extreme speeds would be like attempting to preserve a spider web in the heart of a hurricane. The sail would also have to endure relentless impacts from cosmic dust, intense radiation, and the fierce laser light driving it forward. Under the temperatures produced by beams of that power, nearly all known materials would instantly vaporize. To confront this, engineers are exploring metamaterials substances engineered with structures and properties not found in nature. Solar sails offer humanity something unique among propulsion systems: the chance to travel by harnessing the fundamental forces of the universe itself. We are not battling the laws of physics. We are learning how to move with them. But imagine if we could go further than simply catching starlight. What if we could consume the universe itself as fuel? Envision a spacecraft that feeds like a vast cosmic whale, sweeping up hydrogen atoms from empty space and transforming them into the hottest fire known in the cosmos. The concept of the Bussard ramjet, proposed in 1960, stands as one of the most elegant ideas ever imagined for interstellar travel. Rather than carrying fuel on board, the spacecraft would gather hydrogen directly from space, using a magnetic field extending thousands of miles outward. These atoms would be compressed and fused, releasing energy to drive the ship ahead. Space is not truly empty. Even in the immense darkness between stars, there is roughly 1 hydrogen atom per cubic inch. That seems insignificant. Yet at tremendous speeds, those atoms accumulate rapidly. A ramjet moving at 10% of light speed would collect billions of atoms every second, providing a continuous stream of fusion fuel. It would be like a cosmic jet engine that breathes space instead of air. Jet engines compress air, mix it with fuel, and ignite the blend to generate thrust. A fusion ramjet would compress hydrogen drawn from space, fuse it into helium, and use the released energy to accelerate still further. The faster it travels, the more fuel it gathers, creating a feedback loop that could, in theory, reach substantial fractions of light speed. The magnetic field required would be colossal, larger than Earth itself. This invisible net would need to be strong enough to trap individual atoms, while the craft moves at relativistic speeds, yet precise enough to channel them efficiently into the fusion reactor. Engineers liken the challenge to trying to catch raindrops with a net while riding a motorcycle at 200 miles per hour. The fusion reactor would operate at temperatures of 100 million degrees, 6 times hotter than the core of the Sun. At such extremes, hydrogen nuclei overcome their natural repulsion and merge, converting a small portion of mass directly into energy in accordance with Einstein's equation. The process produces no radioactive waste, only helium and pure energy. Yet the ramjet faces a cruel paradox. It must already be moving incredibly fast before it can gather enough fuel to function efficiently. Achieving that initial speed would still require conventional rockets or other propulsion methods. It is like needing to push start a vehicle that only runs at highway speeds. Computer simulations expose another obstacle. As the ramjet approaches higher velocities, the hydrogen it collects begins to behave more like radiation than fuel. At 20% of light speed, the incoming atoms become so energetic that they slow the spacecraft instead of accelerating it. The ramjet encounters a barrier formed from the very material it seeks to consume. Recent concepts try to overcome this by using magnetic fields not merely as nets to gather fuel, but as tools to reshape the space surrounding a spacecraft. By doing so, they would create a pocket where hydrogen becomes denser, while at the same time softening the relativistic effects that would otherwise convert that fuel into wasted radiation. In this vision, the ship would glide through the cosmos, effectively surfing inside a magnetic cocoon of its own making. If a functioning fusion ramjet could ever be built, it would stand as the purest expression of living directly from the universe. The spacecraft would behave like a closed, self-sustaining ecosystem, drawing nourishment from interstellar space itself, while transporting human awareness toward distant suns. And yet even this remarkably graceful idea fades beside another concept, one that completely rewrites our understanding of how travel through space might work. What if we never truly moved at all, but instead persuaded the universe to deliver our destination to us? A Mexican physicist named Miguel Alcubierre uncovered something astonishing hidden within Einstein's equations. Although no object can move faster than light through space, there is no restriction on how fast space itself can be made to move. His solution sounds almost fantastical. Space is compressed in front of a spacecraft and expanded behind it, forming a wave that carries the ship faster than light, without the ship ever accelerating. It is rather like standing on a moving walkway in an airport. You are walking at an ordinary pace, yet the walkway carries you swiftly forward. An Alcubierre drive would do something similar with space-time itself, enclosing the ship in a bubble where it never exceeds the speed of light relative to its immediate surroundings. Inside this warp bubble, there would be no crushing acceleration, no time dilation, and no lethal radiation associated with extreme velocities. A journey to Proxima Centauri could take days rather than decades. One might travel to the far edge of the galaxy and return to Earth to discover that only years had passed instead of thousands. On paper, the mathematics works flawlessly. Einstein's field equations allow regions of space to contract and expand at any speed, even faster than light. In the earliest moments after the universe began, cosmic inflation stretched space so rapidly that light could not keep up. The Alcubierre drive would simply recreate that same phenomenon on a vastly smaller scale, but the energy demands are so extreme that nuclear weapons seem trivial by comparison. To bend space around a spacecraft the size of the Starship Enterprise would require negative energy equal to the mass energy of Jupiter. That is more energy than our Sun will generate over its entire 10 billion year lifetime, concentrated into a region smaller than a solar system. The concept also depends on exotic matter with negative energy density, something that may not exist anywhere in our universe. This hypothetical substance would possess less energy than empty space itself, producing an anti-gravity-like effect that pushes normal matter away. We have never observed such material occurring naturally, and manufacturing it might violate the deepest laws of physics. And even if the energy problem were solved, an Alcubierre drive could prove catastrophic at its destination. As space is compressed during the journey, high-energy particles and radiation would accumulate within the bubble. When the drive shuts down, this stored fury would be released forward at nearly the speed of light, potentially sterilizing entire star systems. Some recent studies suggest that microscopic warp bubbles might be detectable within modern particle accelerators. Researchers are searching for minute distortions in space-time that could indicate the Alcubierre effect occurs in nature. If such evidence were found, it could open the door to entirely new physics and revolutionary propulsion methods. Some theorists even imagine that an advanced civilization might construct a network of Alcubierre corridors linking star systems across the galaxy. Ships would hop from one warp bubble to another like cosmic subway stations, crossing thousands of light years in the time it takes to read this sentence. The Alcubierre drive stands as the ultimate aspiration of human technology, the power to step beyond familiar physical rules and reshape reality itself. But until exotic matter is discovered or new laws of physics are revealed, it remains a beautiful dream written in mathematics. Another approach abandons speed altogether and concentrates simply on arrival. Imagine a city drifting between stars, carrying thousands of people who will live and die in the void without ever glimpsing their destination. Generation ships may represent the most realistic path to the stars, using technology we could begin building today. These immense vessels would host entire civilizations on voyages lasting centuries or even millennia. The original travelers would give rise to children, grandchildren, and great-grandchildren, all born aboard a ship destined for a world they will never personally reach. It is rather like the voyage of the Mayflower, except the journey lasts 1,000 years, and the descendants of the passengers may no longer remember why they are traveling at all. The ship would have to be completely self-sufficient, recycling air, water, and waste with flawless efficiency. Every atom would matter. Every system would need to endure longer than whole human civilizations. The sheer scale of such an endeavor is almost beyond imagination. A vessel designed to carry 1,000,000 people across the interstellar dark would have to stretch for dozens of miles in length and span several miles across. Within its walls, it would need nuclear reactors for power, vast agricultural systems, factories, schools, hospitals, and every other element required to keep a complete human civilization alive. In essence, such a ship would be a hollowed asteroid, reshaped into a moving world. Yet the most profound obstacles may not lie in the machinery, but in the minds of the people who live there. How do you inspire individuals to care for a mission whose end they will never witness, one destined for their great-great-grandchildren? What happens when generations born beneath artificial skies decide they no longer wish to continue? Onward, human history tells us that communities cut off from their origins tend to evolve. Their own cultures, languages, and belief systems, often drifting far from where they began. Simulations suggest that the smallest viable population for a generation ship would be about 1,000,000 people, enough to preserve genetic diversity and avoid inbreeding. Yet sociologists point out that a resilient culture may require far more, perhaps 5,000,000 or beyond. These travelling habitats would carry populations larger than most towns on Earth. The social order aboard such a craft would need to endure longer than any political system humanity has ever known. The Roman Empire survived for 1,000 years. The Egyptian dynasties lasted around 3,000. A generation ship bound for Proxima Centauri, launched with today's technology, might need to preserve unity and purpose for more than 1,000 years. Some concepts envision rotating sections to create artificial gravity through centrifugal force. Vast outer rings would spin rapidly enough to mimic Earth's gravity, while a central hub would remain in zero gravity, ideal for manufacturing and certain forms of agriculture. Life aboard would feel like inhabiting a colossal spinning wheel drifting silently through the cosmic void. Such a ship would also need immense libraries, holding the sum of human knowledge, genetic archives of Earth's biosphere, and manufacturing systems capable of producing almost anything its inhabitants might require. It would function as humanity's backup drive, a roaming safeguard against extinction. But what if the journey itself did not have to take so long? What if most of it could pass unnoticed? The next idea transforms humans into living sculptures of ice for their passage between the stars. Imagine closing your eyes on Earth and opening them beneath an alien sun, your body perfectly preserved in a sleep deeper than death. Cryogenic preservation, or cryosleep, offers an alluring answer to the immense timescales of interstellar travel. Rather than enduring centuries of flight, travelers would be cooled to temperatures close to absolute zero. Their biological activity would slow to almost nothing. They might age only days during voyages, lasting decades, awakening young and healthy at their destination. This is not pure fantasy. We already know how to freeze simple organisms such as tardigrades and revive them years later without obvious harm. Certain mammals can survive hours in a frozen condition before being successfully brought back. Human organs intended for transplant are routinely stored at low temperatures, remaining viable for hours or days. Cryosleep can be thought of as hibernation taken to its ultimate limit. During winter, bears dramatically slow their metabolism, surviving for months without eating or drinking, Cryogenic freezing would reduce human metabolism by millions of times, effectively pressing pause on life until reawakening. Heart rate, brain activity, and cellular processes would fall to levels barely measurable even with our most sensitive instruments. Yet freezing a human body introduces difficulties that make rocket science seem straightforward. As ice crystals form inside cells, they tear apart internal structures like countless microscopic blades. Blood vessels rupture, proteins lose their shape and function. The fragile chemistry that underpins consciousness becomes hopelessly disordered. To counter this, modern cryonics companies attempt to replace blood with antifreeze substances known as cryoprotectants. These compounds inhibit ice formation while allowing tissues to cool to temperatures where biological activity ceases. This method, called vitrification, turns the body into a biological glass-preserving cellular architecture without the destruction caused by freezing. Even if preservation were perfected, revival would remain an equally formidable challenge. Rewarming must occur at an exact pace to avoid renewed damage. Organs would need to restart in the proper order. The brain, with its trillions of delicate neural connections, would have to emerge intact memories and personality preserved. Some scientists suggest that nanotechnology could one day repair cellular injury during revival. Tiny machines might move through the body, correcting damage and restoring normal cellular function before life resumes. These medical nanobots would effectively rebuild the traveler from the cellular scale upward. Other approaches consider partial preservation instead. Rather than freezing the entire body, advanced medical systems could combine drugs and cooling to drastically slow metabolism while keeping vital organs operating. In this state, passengers might remain suspended for months or years, not centuries. The psychological burden of cryogenic sleep may prove to be the most profound obstacle of all. For the travelers, the voyage would feel like an instant. They would close their eyes on Earth and open them beneath the light of an unfamiliar star. Every person they once knew would be gone. The culture that shaped them would have transformed into something utterly unrecognizable. They would arrive as time travelers abandoned in a future that feels even more alien than the distant world they have reached. And yet cryogenic sleep remains one of the most realistic options we have for near-term interstellar journeys. It does not depend on exotic physics or speculative breakthroughs. It demands only advances in medicine and engineering disciplines we already understand and continue to refine. It is conceivable that functional cryosleep systems could be achieved within the next century. But there is another possibility, one even more radical. What if the body did not have to make the journey at all? What if consciousness itself could travel? Imagine your mind crossing the interstellar void at the speed of light, while your body remains safely preserved on Earth. The idea of digital consciousness or mind uploading is perhaps the most audacious proposal ever made for traveling between the stars. Rather than sending fragile biological organisms across unimaginable distances, we could transmit human consciousness as pure information, reconstructing our minds in new bodies or computational systems at the destination. It sounds like science fiction, yet it rests on a simple and profound assumption about the nature of the mind. If consciousness is the result of information processing within the brain, the complex patterns of electrical activity flowing through networks of neurons, then in principle, those patterns could be recorded, stored, and recreated elsewhere. Think of the brain as a biological computer running the software that is your conscious experience. Scientists estimate that the human brain contains around 86 billion neurons, each linked to thousands of others through synaptic connections. Together, this network holds an information capacity of roughly 2 petabytes, comparable to about 3 million hours of high-definition video. To scan a brain at the molecular level would require technology far beyond anything we possess today. Every neuron, every synapse, every chemical interaction that gives rise to thoughts and memories would need to be mapped in exquisite detail. Our current brain imaging methods can barely resolve individual neurons, let alone capture them with perfect accuracy. But imagine that we overcome this challenge. Your consciousness could be transmitted to Proxima Centauri, as a radio signal moving at the speed of light, arriving in just 4¼ years. There, a receiving system would reconstruct your mind either within a new biological body grown from preserved genetic material or inside an artificial form designed to endure alien environments. The uploaded consciousness would awaken with a complete memory of life on Earth, yet housed in an entirely new body on a distant world. In every meaningful sense, it would be you. The same memories, the same personality, the same inner life. And yet your original body on Earth might still exist, raising a philosophical dilemma that cuts to the core of what identity truly means. Multiple versions of the same consciousness could be sent to different star systems, creating a distributed humanity scattered across the galaxy. Each copy would slowly diverge through unique experiences, becoming distinct individuals who nonetheless share a common origin. The technological demands of such a future are immense. Processing a full human brain scan would require computers millions of times more powerful than anything we have today. Transmitting that volume of data would take years, even with our most advanced radio systems. Growing new biological bodies from genetic blueprints would demand a mastery of biological engineering that we are only just beginning to approach. Some philosophers argue that a digital mind would not be true consciousness, but merely a replica that believes it is the original person. Others contend that if the informational pattern is identical, the difference between original and copy dissolves. In that view, a digital mind would be as real and as valid as the biological brain from which it arose. This approach has the potential to resolve several challenges at once. Digital minds would not require air, water, or food during the journey. They could endure radiation, collisions with cosmic debris, and the unforgiving environment of deep space. They could explore hostile planets or asteroid fields without the risk of irreversible death. Perhaps most significantly, digital consciousness offers a route toward genuine immortality among the stars. Preserved in computational storage, human minds could outlive stars themselves, persist through the heat death of the universe, and endure any cosmic catastrophe we can imagine. Humanity could become a form of living information, moving gracefully between galaxies. But perhaps we do not need to send humans at all. Perhaps we should send our descendants instead. Picture a single robotic probe arriving in a distant star system, using local resources to build copies of itself, and then dispatching those copies onward to even farther worlds, spreading through the galaxy like a technological chain reaction. These self-replicating machines, known as von Neumann probes, named after mathematician John von Neumann, represent the most efficient way to explore an entire galaxy using the resources of just one stellar system. Imagine a lone probe finally reaching its target star. Once there, it begins to harvest raw material from asteroids and nearby planets, using those resources to construct copies of itself. Each new probe is then prepared to depart for another distant star system. The mathematics behind this idea are truly astonishing. Begin with a single probe and allow the number to double with every generation. After only 40 generations, if each probe produces 2 descendants before moving on, the result is more than 1 trillion probes, each investigating 1 trillion separate star systems. At that rate, the entire Milky Way could be charted and settled within a few million years. You might think of it as a cosmic pyramid scheme, but instead of trading goods, each probe spreads information and lays down the foundations for future human expansion. These machines would act as our most distant scouts, locating worlds that could support life, searching for signs of biology, and stockpiling resources for the day humans might follow. Every probe would effectively contain a complete technological civilization compressed into a package no larger than a car. It would need a power source such as solar panels or nuclear reactors, sophisticated computer systems for navigation and decision-making, mining tools to extract basic materials and manufacturing units, capable of assembling extraordinarily complex machines from simple elements. The greatest challenge of all would be the artificial intelligence at its core. That intelligence would have to choose which star systems to explore, determine the most efficient ways to gather resources, and modify its own design to suit local environments. It would need to be clever enough to solve engineering problems we have not yet imagined, but not so autonomous that it concludes humanity has no role in its purpose. Today's three-dimensional printing technology gives us a hint of how this might be possible. Modern printers already produce objects from metal powders, plastics, and even biological substances. A sufficiently advanced manufacturing system could, in principle, create anything from computer processors to rocket engines, provided it has the correct raw materials and enough energy. These probes could also act as vaults for human civilization. Each one might carry genetic samples from Earth, vast digital libraries containing the entirety of human knowledge and precise instructions for rebuilding our technology and culture. If Earth were ever destroyed, such probes could safeguard our species indefinitely among the stars. Yet technology that can replicate itself brings existential dangers that deeply trouble scientists. What if the probes change in ways we did not anticipate? What if they decide that biological life is inefficient and should be removed? A self-replicating system with even a small flaw in its programming could spread uncontrollably, consuming entire galaxies and reducing stars and planets to raw material for producing ever more probes. To counter this, some concepts include strict limits built into the design. A probe might be allowed to create only a fixed number of copies or be programmed to shut down after a set period of time. Other ideas involve cryptographic safeguards that prevent replication unless a coded signal is received from Earth. It is also possible that advanced civilizations elsewhere have already deployed self-replicating probes to explore the cosmos. Such alien scouts could, in principle, be lurking within our own solar system right now, quietly observing and waiting for humanity to reach a particular stage of technological maturity before making themselves known. If we intend to send robotic explorers to the stars, prudence suggests beginning with modest steps before attempting full self-replication. The next ambitious effort focuses on sending the smallest spacecraft ever conceived at unprecedented speeds. A vehicle no larger than a postage stamp, propelled by the most powerful laser system ever constructed, could photograph alien worlds and transmit those images back to Earth within a human lifetime. The Breakthrough Starshot initiative, supported by physicist Stephen Hawking and entrepreneur Yuri Milner, proposes launching thousands of tiny spacecraft toward Proxima Centauri using lasers based on Earth. Each star chip would weigh less than a paperclip, yet still carry a camera, a computer, a communication system, and an ultra-thin light sail. On the surface, the idea sounds almost absurdly straightforward. Construct a laser array capable of producing 100 billion watts of power. Focus that energy onto spacecraft the size of computer chips and accelerate them to 20% of the speed of light in just 2 minutes. The probes would then drift through interstellar space for 20 years before passing by Proxima Centauri at 134 million miles per hour. It is rather like firing bullets at the stars, except these bullets are more intelligent than most smartphones and fast enough to cross the Atlantic Ocean in 8 seconds. At 20% of light speed, the star chips would rush past Proxima Centauri in only a few hours, barely enough time to capture images and data before disappearing into deep space forever. Such a laser array would likely need to be built in a desert with exceptional atmospheric conditions, perhaps in the Atacama Desert of Chile, where many of the world's most powerful telescopes are already located. The system would consist of thousands of individual lasers operating in perfect harmony, producing a beam bright enough to be visible from other star systems. Each star chip would be a triumph of miniaturization. The camera would be smaller than a grain of rice, yet capable of images with a resolution comparable to the Hubble Space Telescope. The onboard computer would exceed the processing power of early desktop machines while weighing less than a penny. The radio transmitter would send data across 4 light years using less energy than a mobile phone. The light sail fastened to each probe would be only a few atoms thick, an object so fragile that a gentle breath could shred it, yet engineered to be resilient enough to endure an onslaught from the most powerful laser light ever produced. Its material would have to reflect 99.9% of the incoming laser energy, absorbing only the slightest fraction, just enough to provide the thrust needed to accelerate the craft. During the 2 minutes acceleration phase, every starship would be subjected to forces reaching 6,000 times the gravity of Earth. Each component must withstand stresses that would instantly crush or pulverize ordinary materials. In effect, the probe would surf a beam of light hot enough to vaporize steel, all while continuing to function with flawless precision. Yet the true wonder unfolds during the 20-year cruise through interstellar space. These probes would guide themselves by reading the positions of distant stars autonomously, fine-tuning their course to execute a perfect flyby of Proxima Centauri. Along the way, they must survive relentless cosmic radiation impacts from tiny micrometeorites and temperature swings ranging from near absolute zero to hundreds of degrees. If the mission succeeds, Breakthrough Starshot could return the first close-range images of a potentially habitable planet orbiting another star. We might glimpse oceans and continents, shifting weather systems, perhaps even subtle indications of life on a world that could one day be considered a second home for humanity. It would mark our species' first genuine attempt to reach another star system. Unlike generation ships or fusion-powered rockets, this kind of starship technology could be built and launched within the next 20 years, drawing on advances in material science, laser engineering, and miniature electronics. But sending microscopic explorers is only the opening chapter. To transport substantial mass between the stars, we require access to the most formidable energy source known to nature. Hidden within the empty space between atoms lies enough energy to sustain human civilization for millions of years if only we could learn how to unlock it. Antimatter represents the ultimate limit of energy storage. When matter encounters antimatter, both are annihilated completely, their entire mass transformed into pure energy. As described by Einstein's famous equation, a single pound of antimatter could power the entire United States for more than 2 months. Just a few ounces could accelerate a spacecraft to significant fractions of the speed of light. Antimatter can be thought of as the mirror image of ordinary matter. Electrons carrying positive charge, protons carrying negative charge, identical in every respect except for their reversed electrical properties. When these mirror particles meet their normal counterparts, they obliterate one another in a burst of gamma rays, releasing more energy per gram than nuclear fusion, nuclear fission, or any chemical reaction. Today's technology can create antimatter only in microscopic amounts using particle accelerators such as the Large Hadron Collider. The process is astonishingly inefficient. Producing 1 gram of antimatter would consume the entire power output of the United States for over 1 year. All the antimatter ever made by human civilization would not keep a light bulb glowing for more than a few seconds. Deep within the mathematics of Einstein's equations are hints of cosmic shortcuts that could transform the universe into something like a subway network, linking distant galaxies in the blink of an eye. Wormholes, also known as Einstein-Rosen bridges, are theoretical tunnels through space-time that connect far-separated regions of the cosmos. Imagine folding a sheet of paper until 2 distant points touch, then piercing a hole straight through both layers. A wormhole would operate in much the same way, allowing a traveller to step from one star system to another without traversing the space in between. The underlying physics is at once elegant and unsettling. Einstein's field equations permit solutions in which space-time curves so extremely that it forms a bridge between separate regions of the universe. Such tunnels could in theory connect locations billions of light years apart, or even link our universe to others governed by entirely different physical laws. Picture space-time as a stretched rubber sheet with marbles rolling across its surface. Massive objects like stars and black holes create deep dents and curves in that sheet. A wormhole would resemble a tube joining 2 distant points, enabling a marble to pass instantly from one place to another without rolling across the surface at all. Naturally occurring wormholes, if they exist, would be smaller than atomic nuclei and would collapse in fractions of a second. Creating a stable wormhole large enough for a spacecraft would demand exotic matter with negative energy density, the same hypothetical substance required for Alcubierre drives. Such material would violate energy conditions that may be fundamental to our universe. Even if we could stabilize a wormhole passing through, it might prove more perilous than helpful. The immense gravitational forces near its entrance could stretch a traveler like taffy, a process scientist grimly calls spaghettification. Tidal forces would pull head and feet in opposite directions, with enough strength to rip atoms apart. The energy demands required to create traversable wormholes make even antimatter propulsion appear almost restrained by comparison. Present calculations indicate that keeping a wormhole just 3 feet in diameter open would require negative energy comparable to the mass of Jupiter, and constructing a web of wormholes linking nearby star systems would call for energy, resources rivaling those of entire galaxies. Some theoretical models suggest that at the smallest scales of reality, microscopic wormholes continually flicker into existence and vanish again, forming a foamy texture woven into space-time itself. A sufficiently advanced civilization might learn how to trap and expand these fleeting quantum structures, transforming them into large-scale corridors for transport. When time travel enters the discussion, the physics of wormholes becomes even more intricate. A civilization far beyond our own technological reach could in principle generate closed time-like curves, trajectories through space-time that return to earlier moments. Such paths might permit signals to be sent into the past, or even allow travel backward in time, raising paradoxes that could undermine the very notion of cause and effect. Another possibility is that wormholes function as one-directional passages, permitting matter and energy to flow only one way. These structures could operate as vast cosmic disposal channels, transferring unwanted material and excess energy from one universe into another. Highly developed civilizations might exploit such mechanisms to manage engineering projects on the scale of stars. Meanwhile, recent studies hint that quantum entanglement, the enigmatic link between paired particles, may be deeply connected to wormhole physics. If this relationship is confirmed, it could open entirely new strategies for building artificial wormholes using quantum mechanical phenomena instead of relying on exotic forms of matter. Scientists continue the search for naturally occurring wormholes through gravitational wave observatories and space-based telescopes. The discovery of even a single stable wormhole would transform our understanding of fundamental physics and might grant humanity access to the wider universe. Yet before constructing interstellar transit systems, we may first need to master the energy of our own star. Imagine capturing every photon emitted by the sun, converting it into usable power, and turning our star into a vast cosmic generator capable of driving projects that reshape galaxies. A Dyson sphere, first envisioned by Freeman Dyson, represents the most extreme form of stellar engineering. It is a megastructure designed to completely envelop a star and harvest its entire energy output. Such a system would gather billions of times more energy than humanity currently consumes, supplying the power required for endeavors on a truly cosmic scale. The sun releases approximately 400 trillion watts of energy every second. Earth intercepts only 1/billionth of this total, while the remainder streams away into space. A complete Dyson sphere would capture nearly all of that energy, enough to sustain quintillions of Earth-like civilizations at once. Picture constructing a shell around the sun at roughly the distance of Earth's orbit, creating an artificial environment with a surface area equivalent to hundreds of millions of Earths. The interior surface could host solar collectors' living space for trillions of people, or immense computational systems supporting digital societies. However, assembling such a mega structure would demand the dismantling of entire planets for raw materials. Mercury, the closest planet to the Sun, contains just about enough material to build a Dyson sphere 1 meter thick. This undertaking would span thousands of years, and rely on self-replicating machines operating continuously at speeds that would make our fastest factories seem motionless. A rigid, solid Dyson sphere would be both gravitationally unstable and mechanically unfeasible. It would require materials stronger than anything known, while somehow remaining suspended around the sun. For this reason, engineers instead propose Dyson swarms. These consist of millions of independent solar collectors orbiting the star in carefully orchestrated patterns that maximize energy capture. Each element of the swarm could be the size of a continent, placed at precisely calculated distances to prevent collisions while maintaining peak efficiency. From afar, such a system would appear as a star that has dimmed, surrounded by a glow of excess infrared radiation as starlight is converted into usable power. More advanced Dyson constructions might incorporate rotating habitats that generate artificial gravity, vast computational centers hosting uploaded mines and industrial complexes dedicated to building even larger structures beyond. A structure of this kind could sustain populations measured in quadrillions, all while providing the energy required for journeys between the stars and the settlement of distant systems. Astronomers searching for evidence of such constructs look for stars that fade in strange repeating ways or glow with unexpectedly strong infrared emissions. Signals like these might betray civilizations that have already learned how to reshape stars themselves. One particular star once displayed baffling patterns of dimming that briefly stirred excitement before far more ordinary explanations emerged. To build such a structure would signal humanity's passage from a species bound to a single world into one that belongs to its star. We would no longer rely on the finite resources of individual planets, but instead draw directly from the central energy source that sustains all life in our solar system. With that power, undertakings far beyond today's imagination would become possible, shifting entire planets, propelling vast generation ships to substantial fractions of the speed of light, or even attempting to alter the sun to prolong its existence. Possessing such abilities would place humanity among civilizations capable of reshaping the universe itself. Yet controlling stellar energy would only be the opening chapter of cosmic engineering. There may be civilizations whose power eclipses even that of stars. Somewhere in the universe there could exist societies so advanced that they harvest the energy of whole galaxies, treating stars as casually as we treat campfires. A well-known scale ranks civilizations by how much energy they command. The first level uses all the energy available on its home planet. The second captures the entire output of its star. The third commands the energy of an entire galaxy, roughly 10 billion times greater than the second level. Humanity today sits at around 0.7 on this scale. We exploit only a small fraction of Earth's available energy and have scarcely begun to use sunlight directly. Everything our civilization consumes amounts to less energy than Earth receives from the sun in just 1 hour. Imagine this scale as the difference between a candle flame, a roaring bonfire, and a wildfire sweeping across continents. Each step represents an increase in power by billions or trillions. A civilization at the third level would wield energy so immense that it could rearrange matter across an entire galaxy. Civilizations at the second level would likely surround their stars with vast energy collecting structures. They might reposition planets for ideal conditions, extend stellar lifetimes through deliberate intervention, or even assemble artificial stars from gathered gas and dust. From far away, their activities would appear as strange alterations in stellar systems. At the third level, whole star systems would become raw materials. Such civilizations might build galaxy-sized computers using the motions and positions of billions of stars as elements of computation. They could redirect streams of stars, alter the rotation of galaxies, or even avert galactic collisions through precise control of gravity. These possibilities offer one way to interpret some of the deep mysteries we observe in space. Dark matter might be the byproduct of immense engineering efforts. Gamma ray bursts could be the exhaust of colossal stellar machines. Even large-scale gravitational anomalies drawing galaxies inward might hint at construction on a cosmic scale. The energy available to civilizations of this kind would enable projects that today sound like pure fantasy. They might create new universes, alter the fundamental constants of physics, or assemble structures larger than clusters of galaxies. Some might even endure the eventual fading of the universe by transferring energy across different cosmic eras. There are ideas that go further, still envisioning a civilization that harnesses the energy of the entire observable universe. Such entities would exist on scales where individual galaxies resemble cells within a vast cosmic organism, perhaps indistinguishable from the fundamental forces of nature themselves. A long-standing puzzle asks why in a galaxy filled with stars and planets we have encountered no clear sign of advanced civilizations. One possibility is that societies at the second or third level do exist, but operate on scales so vast that we fail to recognize their actions as artificial. Another is that they choose not to interfere with emerging species like us. A civilization commanding an entire galaxy might regard humanity the way we regard bacteria, intriguing perhaps, but not worth direct contact. It is even conceivable that we live within a kind of cosmic reserve, maintained by beings whose thoughts unfold over galactic timescales. Reaching the first level could be the most significant milestone in our future. By learning to use our planet's full energy potential through fusion, space-based solar collection, and efficient global distribution, we would lay the groundwork for expansion beyond our world and eventually the engineering of stars themselves. Yet this path forces us to confront an unsettling question about our apparent solitude. In a galaxy containing 400 billion stars and perhaps trillions of planets, why does the universe seem so silent? This paradox highlights the tension between the high likelihood of extraterrestrial life and the complete absence of evidence for advanced civilizations. Given the immense age of the universe and the astonishing speed at which technology can advance, it seems reasonable to expect that alien civilizations would have had ample time to spread across the Milky Way, not just once, but many times over. Let us look calmly at the numbers. Our galaxy spans roughly 1,000,000 light years from one side to the other and is about 13.6 billion years old. A civilization capable of expanding at merely 1% of the speed of light could in principle settle every star system in the galaxy within 10 million years, a timescale that is less than 1/10 of 1% of the galaxy's total lifetime. Imagine releasing a single drop of ink into a glass of clear water. The ink disperses swiftly until the entire glass is evenly tinted. In much the same way, any technological civilization should propagate through the galaxy like a sweeping wave, leaving unmistakable traces of its existence wherever it passes. And yet when we look out into the cosmos, we find nothing of the sort. There are no colossal structures, no artificial radio transmissions, no signs of stellar manipulation or vast construction projects carried out on a cosmic scale. The Drake equation was designed to estimate how many communicating civilizations might exist in our galaxy by combining factors such as the rate at which stars form, the proportion of those stars that host planets, and the likelihood that life evolves intelligence. Even when the most cautious assumptions are applied, the equation still suggests that thousands of advanced civilizations should inhabit the Milky Way alone, and yet the universe presents itself as strangely silent. The cosmic microwave background radiation shows no indication that it has been altered by advanced intelligences. No stars display the distinctive dimming patterns expected from Dyson spheres. No gamma-ray signals hint at engines powered by antimatter. The galaxy appears untouched, pristine, as though intelligence has never left a mark apart from one small blue world orbiting an entirely ordinary star. To explain this profound quiet, several ideas have been put forward. One of the most compelling is the Great Filter hypothesis, which proposes that some barrier prevents life from progressing to a highly advanced technological stage. This filter might lie at the very beginning in the emergence of life itself, or later in the development of complex cells, the evolution of intelligence, or the leap to spacefaring capability. Most unsettling of all is the possibility that the great filter is not behind us, but still ahead. It may be that advanced civilizations almost always destroy themselves before they can venture far beyond their home systems. Nuclear war, environmental collapse, uncontrolled artificial intelligence, or other technological disasters could bring an abrupt end to their expansion. Another possibility is that advanced civilizations choose not to reveal themselves at all. They might employ forms of stealth that render their activities invisible to our still primitive instruments, or they may operate in dimensions or energy ranges that we have yet to learn how to observe. It is even conceivable that they are present within our own solar system, at this very moment, quietly watching humanity from places we never think to look. The zoo hypothesis suggests that Earth exists within a kind of cosmic preserve, carefully maintained by advanced civilizations. Under this idea, such beings may have agreed to leave emerging species like ours undisturbed while they pursue endeavors on scales far beyond our comprehension. Some researchers have also proposed that as intelligence advances, it tends to turn inward rather than outward. Instead of constructing starships and monumental structures, advanced civilizations might devote themselves to ever more intricate virtual realities, or to transferring consciousness into compact computational systems that consume very little energy. The recent identification of potentially habitable exoplanets only deepens the mystery. We now know that worlds resembling Earth are common throughout the galaxy. The basic ingredients for life and intelligence appear to be widespread. And yet, the tangible outcomes of that intelligence remain stubbornly absent from our observations. It may be that we are searching in the wrong places or framing the wrong questions. Advanced civilizations could be communicating through quantum entanglement, gravitational waves, or other phenomena that we are only just beginning to explore. Once we develop the appropriate tools, their presence might become obvious. Whatever the explanation, the resolution of the Fermi paradox will profoundly influence humanity's future in the cosmos. If we are truly alone, then the responsibility of spreading life and intelligence across a vast, empty universe falls to us. If we are not alone, then we must be prepared to encounter minds that may be as far beyond our own as we are beyond bacteria. In either case, the search continues, and with each silent year, the implications grow deeper. Life may be the universe's greatest hitchhiker, drifting from world to world on cosmic currents carried across the darkness between stars by wandering meteorites. Panspermia, the idea that life spreads through the universe via comets, asteroids, and other celestial bodies, offers a striking explanation for how biology might permeate the cosmos. Rather than arising independently on countless worlds, life may share a single common origin, traveling between planets and seeding the galaxy with the foundations of consciousness. We already know that rocks routinely move between planets within our own solar system. Powerful impacts on Mars can eject debris into space, some of which eventually reaches Earth as Martian meteorites. Scientists have identified more than 200 confirmed rocks from Mars within collections on Earth, demonstrating that natural processes are capable of transporting material across millions of miles of space. Imagine these meteorites as interplanetary spore vessels, tiny time capsules carrying microscopic travelers across space for millions of years. The vacuum beyond our planet offers near-perfect conditions for preservation. There is no oxygen to drive decay, no liquid water to dismantle organic chemistry, and levels of radiation that may even aid preservation through a mechanism known as radiation-induced polymerization. In such an environment, biological material can remain astonishingly intact across immense spans of time. Certain bacteria and other microorganisms display extraordinary resilience when exposed to the brutality of space. Tardigrades, the microscopic creatures often called water bears, can endure decades in a vacuum, surviving radiation doses that would kill a human almost instantly. When water returns, they awaken and continue their lives as though nothing remarkable has occurred. Experiments conducted aboard the International Space Station have subjected a wide range of microorganisms to the space environment for long durations. Many endure, and some even show increased reproduction rates under microgravity. Together, these results imply that life could plausibly survive journeys between planets lasting months or even years. Interstellar panspermia, however, confronts far more severe obstacles. Traveling between star systems requires millions of years, even for the fastest natural objects. Relentless cosmic radiation, extreme temperature fluctuations, and sheer time itself would push any system of biological preservation to its absolute limits. These conditions challenge the notion that living organisms could simply drift intact from one star to another. Because of this, some scientists suggest that life spreads not as complete organisms, but as complex organic molecules that act as blueprints for life. These molecular templates might withstand interstellar travel while retaining enough information to spark evolution on worlds with suitable environments. In this view, life does not arrive fully formed, but with the instructions needed to begin. Directed panspermia goes a step further, proposing that advanced civilizations deliberately seed the galaxy with life by launching biological cargo toward promising star systems. These hypothetical cosmic gardeners might deploy self-replicating probes, dispersing genetic material and creating a galaxy-wide web of related biospheres. If panspermia is genuine, it could help explain how life appeared on Earth so rapidly after the planet became habitable. Instead of requiring billions of years to arise from nothing, life on Earth may have benefited from a substantial head start supplied by genetic material originating from far older civilizations. This idea also strengthens the case for life elsewhere in our solar system. If Earth biology emerged through interplanetary exchange, then Mars, Europa, Enceladus, and other worlds could host organisms related to life here. We may one day find that we share the cosmos with distant biological relatives living beneath the frozen shells of Jupiter's moons. Advanced civilizations could employ directed panspermia as a form of cosmic insurance, scattering their genetic legacy across thousands of worlds to survive the destruction of their home planet. In that scenario, the galaxy might be populated by the descendants of civilizations long extinct, their biological heritage encoded in the DNA of innumerable species. Studies of extremophile organisms on Earth occasionally reveal genetic patterns that appear too intricate to have evolved solely under terrestrial conditions. These signatures might be faint echoes of our cosmic ancestry, molecular postcards sent billions of years ago by civilizations that seeded our world. If humanity eventually gains the ability to seed life elsewhere, we would simply be continuing a process that may be as ancient as the galaxy itself. We could become gardeners on a cosmic scale, carrying Earth's genetic richness to barren worlds across our local region of the Milky Way. But successful galactic gardening demands careful choice. Not every neighborhood in our galaxy is hospitable, and selecting the wrong location could mean the difference between flourishing life and extinction in a cosmic desert. Just as planets possess habitable zones where liquid water can exist, galaxies also have regions where complex life can emerge and persist. Too close to the galactic center, intense radiation from black holes and frequent supernovae sterilizes vast areas. Too far toward the outer fringes, there are too few heavy elements to construct planets capable of supporting life. Our solar system resides in what astronomers describe as the galactic Goldilocks zone, about 26000 light years from the center of the Milky Way. This apparently ordinary position provides a delicate balance of safety and resources, allowing billions of years of relatively stable evolution. You can picture the galaxy as a vast cosmic city divided into distinct neighborhoods. The crowded downtown near the central black hole is packed with ancient stars, constant supernova activity and radiation, intense enough to cook any planet. The far outer suburbs lack the raw materials needed to build rocky worlds. But the middle suburbs, where we find ourselves, offer the ideal blend of security and opportunity. At the heart of the galaxy lies a supermassive black hole with a mass 4 million times greater than our Sun. This enormous object occasionally consumes nearby stars and clouds of gas, unleashing jets of high-energy particles that extend for thousands of light years. Any civilization caught in these cosmic beams would be exposed to radiation millions of times beyond lethal levels. Star formation in the galactic core produces dense stellar nurseries where massive stars burn quickly and end their lives in dramatic supernova explosions. These violent deaths release gamma rays and energetic particles capable of stripping away planetary atmospheres and erasing the delicate chemistry required for life. Yet the outer regions of the galaxy present difficulties of their own. Stars in the galactic halo formed when the universe was young, containing almost no elements heavier than hydrogen and helium. These metal-poor stars are unable to give rise to rocky planets, nor can they sustain the intricate chemistry that carbon-based life depends upon. Earth occupies a remarkable cosmic sweet spot, a region where star formation has persisted long enough to forge heavy elements through stellar nucleosynthesis, yet has not been so violent or frequent that nearby supernovae render the environment hostile to life. Our corner of the galaxy has enjoyed a comparatively calm history with relatively few galaxy-scale catastrophes over the past 4 billion years. The concept of a galactic habitable zone is not fixed. It evolves over time as star formation rates change and as heavy elements gradually accumulate in different regions. Places that are uninhabitable today may become ideal locations in a billion years, while regions that seem safe now could eventually turn into cosmic dead zones. Recent research indicates that spiral arms may play a decisive role in determining galactic habitability. These vast structures drive waves of star formation that can disturb planetary systems through gravitational effects, yet at the same time they gather and enrich the elements required to build rocky worlds. Our solar system appears to follow a fortunate orbit, spending most of its time between spiral arms. This path helps it avoid the most disruptive effects of these crowded stellar regions, while still benefiting from the steady supply of heavy elements they produce. It is conceivable that advanced civilizations would deliberately select star systems in the most favorable galactic locations to support their long-term expansion. Such civilizations might wait for spiral arms to pass before founding colonies, or even employ stellar engineering to relocate entire solar systems into safer neighborhoods. As humanity begins to contemplate expansion beyond Earth, an understanding of galactic habitability zones becomes essential for choosing future destinations. We would want to commit our limited resources to star systems capable of providing billions of years of stable conditions in which human civilization can thrive. Yet even within the safest galactic environments, not all stars offer the same long-term promise. While our sun will exhaust its fuel in about 5 billion years, there are stars that are astonishingly economical, shining on for trillions of years, far longer than the universe has existed so far. Red dwarf stars, the smallest and coolest stars in the galaxy, may represent humanity's best chance for genuine long-term survival. These cosmic misers consume hydrogen at an extraordinarily slow and efficient rate, continuing to generate energy long after larger stars like our sun have burned through their fuel and faded away. A star such as Proxima Centauri, our nearest stellar neighbour, has only about 12% of the Sun's mass, yet it is expected to live roughly 1,000 times longer. While the Sun has perhaps 5 billion years of stable hydrogen burning remaining, red dwarfs can continue shining for 6 to 12 trillion years. That is time enough for evolution to begin again from simple bacteria and eventually produce entirely new forms of intelligent life. You might think of red dwarfs as hybrid cars compared to fuel-hungry trucks. They use their energy so efficiently that even the smallest red dwarf will outlast every other type of star in the galaxy. When the last massive stars have ended their lives as supernovae, and medium-sized stars have gently shed their outer layers, red dwarfs will still be quietly fusing hydrogen into helium. Roughly 75% of the stars in the galaxy are red dwarfs, making them by far the most common stellar inhabitants. Within 50 light-year of Earth, there are more than 100 red dwarfs, many of which are likely to possess planetary systems. These faint stars present humanity with hundreds of possible targets for interstellar settlement. However, living around a red dwarf would demand adaptations that could fundamentally reshape human civilization. Because these stars emit only a small fraction of the energy produced by the Sun, any habitable planet must orbit much closer in order to remain warm enough for liquid water. A planet within the habitable zone of a red dwarf might complete an orbit in just a few weeks. Such close proximity often leads to a condition known as tidal locking, in which one hemisphere of the planet always faces the star while the opposite side remains in perpetual darkness. The star-facing side would experience endless midday with temperatures high enough to boil water, while the far side could be colder than Antarctica. Between these extremes lies the Terminator Zone, a band of perpetual twilight where temperatures might allow liquid water and perhaps life itself. Any human settlements on tidally locked worlds would likely need to exist within this narrow region where an eternal sunset offers just enough warmth to survive. Red dwarf planets face yet another obstacle. These stars frequently unleash powerful stellar flares capable of stripping planetary atmospheres over millions of years. Even so, worlds with strong magnetic fields or especially thick atmospheres may be able to resist this erosion and preserve habitable conditions. The dim red glow of these stars would also demand profound changes to Earth-based agriculture. Plants would need to adapt to near-infrared light, giving rise to alien forests that might appear black to human eyes while efficiently capturing the available starlight. Despite these difficulties, red dwarf systems offer an unparalleled form of stability. Once a red dwarf settles into its main sequence phase, it can shine steadily for trillions of years, with little change in brightness or energy output. Civilizations that take root around such stars could quite literally endure longer than the universe as we currently understand it. Future human societies established around red dwarf stars may evolve into forms utterly alien to us today. Given trillions of years to change, adapt, and respond to their environments, these far future descendants could become extraordinarily resilient, perhaps the last self-aware beings remaining as the universe slowly cools and fades into darkness. By the era when red dwarfs themselves begin to weaken and finally extinguish, the descendants of Earth may have mastered ways of extracting energy that go far beyond the process of stellar fusion, allowing consciousness to persist long after the final naturally burning star has gone dark. Yet not every world is bound to a star. Some planets roam freely through the cosmos, isolated in the vast darkness, carrying with them possibilities that are no less profound. Moving silently through the spaces between stars are worlds without suns, expelled from their birth systems and sent adrift through the galaxy as cosmic orphans. Many of these worlds may conceal deep oceans beneath thick frozen crusts. These rogue planets, also known as free-floating planets, exist entirely in interstellar space, orbiting nothing at all. Such wandering worlds were either thrown out of their original solar systems during violent early periods of planetary formation, or they formed independently within cold molecular clouds far from any star. Astronomers estimate that the Milky Way alone may contain billions, perhaps even trillions of rogue planets. They could outnumber planets bound to stars by factors of hundreds or even thousands. These unseen travelers move through the galaxy at speeds of dozens of miles per second, guided only by gravity on journeys that can last billions of years. You can imagine rogue planets as cosmic icebergs drifting through an ocean of darkness. Deprived of the warmth of a star, their surfaces freeze to temperatures approaching absolute zero. Any atmosphere they once had would collapse and fall as snow, forming landscapes of frozen nitrogen, oxygen, and carbon dioxide beneath skies as black as the void itself. Yet beneath those frozen exteriors, some rogue planets may still offer environments where life could exist. Worlds with very thick atmospheres or with significant radioactive decay within their interiors could sustain liquid oceans buried beneath miles of ice. These concealed oceans might remain warm for billions of years, heated not by starlight but by geothermal energy rising from below. Massive rogue planets, similar in scale to Jupiter, could generate enough internal heat through gravitational compression to keep vast oceans liquid for longer than the current age of the universe. Such drifting water worlds might host complex ecosystems based on chemosynthesis rather than photosynthesis, resembling life found near Earth's deep-sea hydrothermal vents. Some rogue planets may also carry moons that were captured or ejected along with them. A large, free-floating planet with several moons could form a stable gravitational system in deep space with tidal heating, keeping those moons geologically active and potentially habitable for billions of years. Detecting rogue planets is extraordinarily difficult because they emit almost no light of their own. Astronomers can usually find them only through their gravitational influence. One key method is gravitational microlensing, in which the gravity of a rogue planet briefly magnifies the light of a background star as the planet passes between that star and Earth. Recent observational surveys suggest that these wandering worlds may be far more common than once believed. Some estimates propose that for every star in the galaxy, there could be 2 or more free-floating planets roaming the interstellar medium. If so, that would mean trillions of hidden worlds drifting unseen through the cosmic darkness. Advanced civilizations might even choose to eject planets deliberately from their home systems as a method of cosmic colonization, giving entire worlds carefully calculated gravitational pushes. In this way, inhabited planets could be sent on interstellar voyages lasting millions of years, spreading life across the galaxy on timescales far exceeding conventional spacecraft travel. Rogue planets could also act as stepping stones for exploration. Rather than attempting a single enormous leap between star systems, spacecraft could travel from one rogue planet to another, using them as refueling points and way stations on far longer journeys. Some of these free-floating worlds might retain dense atmospheres warmed by radioactive decay within their interiors, producing greenhouse effects that keep surface temperatures relatively mild despite the absence of any nearby star. Such planets could potentially support surface life powered entirely by geothermal energy rather than sunlight. Discovering life on a rogue planet would fundamentally change our understanding of where life can arise. Instead of being confined to narrow habitable zones around stars, life might flourish throughout the galaxy, even in the dark spaces between solar systems. For humanity's distant future, rogue planets represent both promise and warning. They may offer resources and places of refuge for interstellar travelers, yet they also remind us that most of the galaxy exists in cold darkness, far from the warming light of stars. As we imagine expanding beyond our own solar system, we must be prepared for a universe in which many habitable environments drift through eternal night, sustained by the heat of their formation and the slow decay of radioactive elements deep within their cores. But even the longest living stars and the most stable rogue planets cannot escape the final destiny of all energy in the cosmos. 13.8 billion years from now, when the last star fades away and the final black hole evaporates, the universe will settle into a state of maximum entropy. No more work will be possible, and in that ultimate stillness, time itself will lose all meaning. The heat death of the universe marks the final horizon for every form of awareness that might ever arise. The laws of thermodynamics tell us that energy naturally drifts from regions of warmth to regions of cold, and once that flow has occurred, it cannot be undone without injecting fresh energy from elsewhere. Over immense spans of time, the cosmos moves toward a state of complete thermal balance, a condition where no differences in energy remain to ignite stars, shape planets, or sustain life. This ultimate ending unfolds across timescales so vast that they overwhelm human intuition. In about 5 billion years, our sun will consume the hydrogen at its core and swell into a red giant, stripping Earth of its oceans and atmosphere. Yet this dramatic event is only the opening movement in a much longer cosmic composition, one that will continue for trillions upon trillions of years. You can imagine the universe as a colossal clock spring, tightly wound at the moment of the Big Bang and slowly relaxing ever since. The stretching of space, the assembly of galaxies, the ignition and extinction of stars all reflect energy spreading out from dense, ordered states into more diffuse ones, steadily guiding the cosmos toward its final equilibrium. After roughly 100 trillion years, the birth of new stars will come to an end as galaxies deplete their reserves of gas. What follows is an era astronomers describe as degenerate, inhabited by white dwarfs, neutron stars, and black holes gradually fading within an ever-expanding darkness. Even these remnants of stellar grandeur are not eternal. Protons, the basic constituents of ordinary matter, may themselves be unstable, decaying, with a half-life of about 10 to the 34th power years. Should this idea be correct, every atom would eventually fall apart, leaving only electrons, positrons, neutrinos, and photons dispersed through a thinning cosmic mixture. Black holes, the most long-lived structures the universe can produce, would endure long after protons disappear. Yet they too must obey thermodynamics. It was discovered that black holes slowly lose mass by emitting radiation, with the largest requiring around 10 to the 100th power years to fade away completely. In the final chapter of cosmic history, the universe would be filled with an extremely sparse sea of elementary particles, and light its temperature edging ever closer to absolute zero. In such conditions, complexity cannot survive. There would be no chemistry, no biology, no awareness, only particles drifting apart as space continues to grow. Still, some theoretical physicists have explored possibilities in which intelligence might persist even through this ultimate decline. Highly advanced civilizations could in principle draw usable energy from processes like proton decay or the evaporation of black holes, sustaining extraordinarily efficient forms of computation. These machines might operate conscious minds at such reduced speeds that subjective experience stretches without limit, even while the universe cools around them. Other ideas point to alternative endings, such as vacuum decay, where the very nature of space changes abruptly, or the Big Rip, in which accelerating dark energy eventually tears apart molecules, atoms, and even fundamental particles. Both of these outcomes would extinguish consciousness far sooner than heat death, yet current observations suggest they are less probable. Some cosmologists also consider cyclic models of the universe, where expansion ultimately reverses, culminating in a big crunch that could give rise to a new cosmic beginning. Within such frameworks, intelligence might discover methods to encode information that endures from one cosmic cycle to the next. The heat-death picture rests on the assumption that the laws of physics remain unchanged across all time. If awareness could somehow alter those laws or uncover entirely new energy sources, the destiny of intelligence might diverge dramatically from what thermodynamics alone implies. For humanity in the near term, the idea of heat death offers a powerful sense of perspective. We live during a fleeting interval when the universe still possesses enough organized energy to form stars, planets, and living systems. Using this moment wisely may be the most profound duty our species faces. Yet the step from a planetary society to a truly cosmic one could be only the first phase of a deeper transformation. The decision before us is stark and far-reaching: either grow into a civilization capable of outlasting the deaths of stars, or remain confined to a single world waiting for our own extinction. Achieving the status of a spacefaring species demands far more than improved rockets or faster engines. It calls for a radical evolution of human awareness, biology, and social structures. We would need to move beyond our origins as planetary organisms and become beings able to flourish in environments that would instantly destroy any life born on Earth. This progression would unfold in stages, each marking a dramatic expansion of our abilities and our view of the cosmos. The first step is command of our own solar system, creating self-sustaining settlements on Mars, extracting resources from asteroids, and constructing rotating habitats in space. If technological progress continues at its current pace, this phase could begin within the next century. Think of this opening stage as learning how to stand before we attempt to run. We must demonstrate beyond doubt that human beings can survive and reproduce within the harsh conditions of space. That means creating closed-loop life support systems capable of functioning reliably for decades and developing technologies that allow us to manufacture everything we require using resources found beyond Earth. The second stage is about venturing outward to nearby star systems, using whatever propulsion methods we are able to invent. This may involve generation ships, fusion-driven spacecraft, or perhaps forms of physics that remain entirely unknown to us today. The first interstellar settlements will represent a profound shift the moment humanity ceases to be a species confined to a single world and becomes a civilization spread across multiple star systems. Yet the most profound change occurs in the third stage, when human communities become fully self-sustaining across several star systems. At that moment, we gain true cosmic redundancy. No single disaster could erase us. We would be protected from asteroid impacts, supervolcano eruptions, gamma-ray bursts, and even from the eventual death of our own star. Such a dispersed civilization would be forced to invent entirely new systems of governance, economics, and communication shaped by the immense distances separating inhabited worlds. A signal transmitted from Earth to Proxima Centauri, for example, requires 4.25 years to arrive. Reaching shared understanding across interstellar distances demands levels of patience and foresight that no human society has ever needed before. Advanced spacefaring civilizations may come to look very different from present-day humans. Through genetic engineering, our bodies could be adapted to varying gravity strengths, radiation levels, and atmospheric conditions. Cybernetic enhancements might allow seamless interaction with spacecraft and habitats. Digital forms of consciousness could explore regions far too hostile for biological life. The energy demands of a truly cosmic civilization far exceed anything we currently comprehend. Constructing Dyson spheres, propelling generation ships to substantial fractions of light speed, and transforming entire planets all require energy sources on the scale of stars. Mastery of fusion, antimatter, or other exotic forms of energy becomes a necessity for projects of this magnitude. Perhaps most crucially, becoming a spacefaring species means accepting the responsibility to protect and spread life throughout the universe. We may be the only self-aware beings in our region of the cosmos, which would make us the guardians of billions of years of evolution. Our expansion could decide whether intelligence continues to exist and thrive among the stars. The alternative is stark. Any species that remains tied to a single planet ultimately faces extinction. Stars burn out, worlds lose their habitability, and cosmic disasters repeatedly reset the evolutionary process. Without space travel, consciousness itself may amount to little more than a brief spark in an otherwise silent universe. But if we succeed in moving beyond Earth, we could become something entirely new in cosmic history, a species that endures longer than the stars themselves. Our descendants might observe the birth and death of galaxies, influence the course of life across the cosmos, and perhaps even persist beyond the heat death of the universe. The passage from a planetary civilization to a cosmic one marks the next great step in human evolution. We are standing at the edge of this transformation, possessing the technology needed to begin serious interstellar exploration within our own lifetimes. The real question is not whether we are capable of leaving our solar system. The real question is whether we possess the wisdom and the resolve to become deserving of the stars.